extra books and things.
Nice.
So, all right, here we go. All right, class, attention up here, please. Thank you. All right, so what we're looking at are some situations where we're going to have to use vectors in order to solve this. Has anybody ever seen done any slacklining?
Yeah.
Where you've got like this rope in between like two like poles or posts, something like that, and then you like kind of try to walk on it. Okay, Nick, you know there's an episode of The Office,
That's what I
right,
just said.
where Andy goes and they go and he comes back and he says, "Oh, yeah, I saw something, a slackline, and it's a team building thing." Right, and so then they do it, try to in the parking lot. Okay, so here we have someone who's slacklining, trying to walk across this this rope or maybe sort of like sort of cable or type of thing, and they're standing still, and this person apparently weighs 60 newtons, pulling down. The rope here has tension, which is pulling it up at a 21-degree angle from the negative x-axis, and then over here 25 degrees from the positive x-axis. And so that's kind of the situation. What this the question is asking is find the tension in the cable to the left of the object. So that would be what is the tension here, the force that is pulling it up, and what is the force over here that is pulling it up to the right. We can see there must be forces there, otherwise this object would be slowly falling down or very quickly falling down. There's got to be something holding it up. Right now this object is totally stationary, static. Okay, it's not moving. So what we can imagine is that this point right here is the point at which all three of these forces are acting. 60 degrees down, however many, or 60 newtons down, however many newtons up into the left, we'll just call that L, and however many newtons up and to the right at 25 degrees. So it's literally three forces acting together, and all of those forces add up to equal 0. Okay, sound familiar? If you remember what we did last Thursday, it's almost exactly the same. What we're going to do is we're going to say L plus R plus that 60, and we'll say this. We'll break them down into their x and y parts, and then we'll say the summation of the forces in the x direction equals 0, and the summation of forces in the y direction equals 0. That'll give us two equations, two unknowns. We'll solve them, graph them. That point of intersection is going to tell us what that left and R values are. Okay? So, over here, we'll write our vectors L, which has a magnitude of L, we don't know, at an angle of 21 degrees, if we could say north of west. That's one way you could write it. If we wanted to, we could do 180 minus 21. It doesn't really matter. I think that's fine for us right now. So we'll break that down into its x and y components. So Lx, these formulas, roll off your tongue now. Magnitude, cosine theta. All right, yeah. So L cosine 21 degrees. Ly is magnitude sine theta. All right, so L sine 21 degrees. Will either one of those be negative? Lx is going to be negative because we can see it going to the left. So I'll push my side. So there you go. If we, and just as a reminder, if we had subtracted that 21 from 180 and got, what was it, 159 or whatever it was, then it would, and we did the cosine, then it would actually yield the positive or negative. We wouldn't have to mess with it. But since we're dealing with the acute angles there, we do that ourselves. Okay. So vector R has a magnitude of R at an angle 25 degrees. I'll just leave it as 25 degrees because that's written in standard degree form, which means we're in the positive x-axis. Rx, magnitude cosine theta. Ry, magnitude sine theta. So R cosine 25, R sine 25. Should either one of those be negative? Not for the R, because it's going up to the right and up. And let's call this 60 Newton vector that's down, we'll call that the weight, since that's apparently what it is. So the weight vector is a magnitude, this is nice, they actually told us that it's a magnitude of 60 degrees, or sorry, of 60 newtons. What direction should we say? South? We could say south, but I'd rather put a number there. What's that? 0? We could say 0 degrees in the direction of south, but that's not normally a standard way. Normally 0 would be straight east. How would we reference that standard in standard angle notation?
Would it be 90?
270 sounds fine.
70.
You could say 90 degrees south of east or something like that, or a 270 is not bad. WX, magnitude cosine, so 60 cosine 270. WY, magnitude sine theta, so 60 sine 270. Let's use our brains here for a moment. Should either one of those be negative? Which one? Not both of them.
Just the Y.
Just the Y. Alright? Now, this is kind of a special case because it's exactly straight south. We can probably also, using our heads, figure out what the X component is. Rosa? It's 0. If you weren't sure of that, or you kind of like, I don't know if I trust my mind on that way, you could always just type this into your calculator and you'll get 0. Cosine of 270 is 0. We probably could also use our head and figure out what the Y component is. Not negative 0. It is negative. Nope, that's more than just 1 Newton downward. It's exactly 60 newtons downward. Let's make it a nice 60. Negative 60. I'm writing this out because it's going to make my life easier when I expand these, write these formulas down. I don't want to write negative 60 sine 270 if I can just write negative 60. And I don't want to write 60 cosine 270 if I can just write 0 or nothing, because it's not going to matter. Okay? So now we're going to write our two equations, summing the forces in the x direction and in the y direction. So here we go. Summation of forces in the x direction. That's going to be Lx, Rx, and Wx. So Lx negative L cosine 21 degrees plus R cosine 25 degrees plus 0 equals 0. Let's go ahead and solve for either L or R. Student's choice. Say again?
L.
Solve for L, okay? So I'm going to get that L all by itself, which means I'm going to subtract R cosine 25 from both sides. So I'll say L equals minus R cosine 25 degrees from both sides. Then I need to get rid of this cosine 21 degrees, which is being multiplied by the L. So I'll divide by cosine 21 over there, divide by cosine 21 over here. Actually, I'm going to divide by negative cosine 21. Do y'all see that? Because I've got a negative right there. Sounds good to me. Now, a negative over a negative is a positive, so maybe you can cancel those out. There you have. L equals R cosine 25 over cosine 21. That's our first equation. Our next equation is going to be the summation of forces in the y direction. So this one, and this one. So we'll write L sine 21 degrees plus R sine 25 degrees minus 60 equals 0. We did all this last Thursday. Do you remember that? It's a lot faster now that we kind of know what's going on. We're going to continue to solve for L, just so that we have L equals and L equals. So I'm going to add 60 to both sides. Subtract r sine 25 from both sides. And then divide both sides by the sine of 21 degrees. Then I'm going to change the L and the R to X and Y's. So I have L equals, I'll just change that to Y equals. And I have R, which I'll change to X. And then everybody, as an activity real quick, let's go ahead and type that into Desmos, and we'll find out that X, which equals R, equals some value, and Y, which equals L, is another value. Round to the nearest 10, find the point of intersection. That point of intersection is where both equations are true, which is the L and R values, which make the summation of those vectors 0. So walk around, I want to see intersection lines. Did you also leave your check the answer that you get with the answer on the back of the packet. Shut it down.
Yeah. Yeah. No, it's just
Just takes a little bit.
I don't know because they got it, but I don't know. I'm trying a different time. I know. I tried 3 times. Did you get anything to load?
It should not have negative values.
It's the website. Go to Google and try that.
Remember, you want to make sure you're in degree mode by going to the wrench in the top right corner and then change to degrees. Alright. Yeah, some of y'all it's not working. For some of you it is working. That's fine. But you've used it before, right? You type it in. Make sure you're, are we in the right answers?
Yeah.
If you're not getting the right answers, it's either because Desmos isn't loading, because there's some problems with that, or because you're not in degree mode, okay? Are y'all comfortable moving on from this, though?
Yes.
I think we're fine. I think y'all know how to do this. Let's go ahead and look at the last problem. And Nick, go ahead and read that to us. A box weighing.
A box weighing 400 pounds hangs from 2 cables, as shown in the variable. Find tension in each cable. Carry your intermediate solicitation to at least 4 decimals of the cable. Round your final answer to the answer.
Alright, the good news is we don't need to worry about rounding answers and stuff like that because we're going to use Desmos again on this one. Although we can just, we'll fast forward, we'll just set it up and then be done with it. So here we have some box being supported by a rope over here and a rope over here, and those cables or ropes or whatever are not forming the same angle. Okay, we've got a 30-degree angle, 47-degree angle. What we want to do is we want to identify a point on this system where all those forces are acting. And you might guess that this point right here is a great location to think about. Because that point right there is going to feel the 400-pound force pulling straight down. But that's not all. It's also being pulled up a little bit. Actually, it's being pulled up the exact same amount that it's being pulled down. Let me say that again. It's being pulled up exactly the same amount that's being pulled down. How do I know that? Because what? It is still. Yes, you're right. Because that's, in fact, it's also being pulled to the left and being pulled to the right. But it's being pulled to the left and the right also, again, at exactly the same amount. So that if you were to add them up, if you add all the lefts and add all the rights up together, then it equals 0. Because they cancel each other out. Same thing with the ups and downs. So the thing is, though, that the 47 degrees is up there, and I want to know, I don't want to know that angle, I want to know this angle as if I were to sort of, I want to know this angle from the negative x-axis. Right? Now, let's go ahead and channel your geometry spirit here. Do you remember in geometry when you had parallel lines like that, cut by a transversal, there was a special name for angles that looked like that?
Alternate interior.
Alternate interior. Good memory.
Great job. I was like complimentary.
You're probably thinking corresponding.
Yeah.
But yeah, alternate interior angles. So the interior and they're on alternate sides of that transversal. Does anybody remember what the relationship was between alternate interior angles on parallel lines?
They're equal.
They equal 180. They do not equal 180 because they're clearly both acute. You might say they add up to equal 180, in which case they're supplementary, but that was not the situation. In fact, actually what it was, don't they look kind of the same?
I was gonna say, yeah, they're the same.
They are congruent to be geometric, alright? So, hooray for us, 47 degrees. Also right over here, same idea. Parallel lines cut by a transversal, that 30 degrees, and this angle right here are both 30 degrees. Which tells us that once again, if I draw the picture over here, what's called the free body diagram, I have tension in the rope going to the left, I'll call that force L at 47 degrees. I have tension in due to the rope R at 30 degrees, and I have 400 pounds of a force straight down. It's not moving at all. The way that you would solve this problem is exactly like the one that we did before. You would break L down into its x component, y component, R into its x component, y component, the weight into its x component, y component, sum up all the x's, set equal to 0, sum up all the y's, set them equal to 0, graph it on, solve for y, graph it on Desmos, find the point of intersection, and you're done for your L and your R. So a very similar problem, just sort of adding a picture, giving you a context for that problem. Sound good? Any questions? All right, 1 minute break till the video.